Old houses like my parents' home comes wired with simple electromechanical doorbells. They are a simple electromagnet with a metal rod that when energized gets pulled to one side and hits a metal plate, like a vibraphone. When the power is cut, a spring on the other end of a rod will accelerate it to the other direction and hits another plate. These plates generally emit different tones when hit. That's why these doorbells are known for their shine. That's all there really is to it. Not that I'm throwing shade at this technology for its simplicity, in fact, simple is definitely better, all else being equal. But these dumb ding-dong machines are hard to expand on. Adding another chime somewhere else in your house will require a ton of wiring that will be hard to hide and expensive once you realize the mess you made and call someone else to repair it. Modern approaches like Nest Hello or Ring Video will require you to gut all of your system and replace it with proprietary hardware and protocols, not to mention the elevated price tag, the questionable privacy, and perhaps redundant camera on the doorbell. Don't get me wrong, it is a good deal if you want something to work right off the box, but they are not exactly what I was looking for. You see, my dogs are getting old, and now you can rely on them to warn you when someone is ringing the doorbell, especially while everybody else is watching the game. Adding another chime will be the easiest solution, but there simply wasn't a pretty way to place cable all the way to the living room. And even then, a chime might not be heard in the middle of a goal and it will definitely disturb your VG session. But how would you notify someone that the doorbell is ringing without being intrusive or ignored? Well, you could make a sign that lights up whenever someone rings the doorbell, but that's easier said than done. So in this series of videos, we will build just that, a Wi-Fi-enabled, smart and visual doorbell system that will light up a sign whenever someone rings the doorbell, as well as many other IoT features that can be coded in. In this first video, we will focus on building a working prototype of the sensing part of the system, the doorbell sensor. The sign and other aspects of the project will have their own video. To tackle this, it is a good idea to define exactly what we need. Let's start with the basics, then we will add additional features and characteristics as we go along. First and foremost, we need a way to detect when someone is ringing the doorbell. Secondly, the microcontroller needs to process the signal and communicate with the sign. And finally, the microcontroller needs to be able to run on batteries for a long time. This breaks up the design into three problems we can solve: detection, communication, and power. For the first problem, there are multiple ways to check if someone is ringing the doorbell. You could sense the loudness of the plates with an acoustic sensor, or the movement of the rod, or even the strength of the magnetic field of the coil, for example. For multiple reasons, the more reliable way to check if someone is ringing the doorbell is sensing the voltage at the coil. In my case, the doorbell solenoid is operated at 120 volts AC. This may be different on your house. A simple and compact way to detect an ASIC signal is to build a simplified transformerless power supply. Transformerless power supplies, or TPSU, are what's typically used in compact low-power applications like smart relays and many other IoT devices. They work in a similar fashion to regular power supply, but instead of relying on a transformer to lower the voltage to a usable level, they use the reactance of a capacitor, also known as X, to cause a voltage drop without dissipating any extra heat in the process. Ideally, of course. The mathematics behind this can get a little bit complex and subject to another video. In the meantime, you can refer to this hack of the article linked in the description. After lowering the voltage, rectification and regulation is done in a similar fashion as traditional power supplies. Because we don't need the power supply to supply stable power, we can make a few compromises that will enhance several characteristics of our design. For example, the filtering cap should be designed to be small enough to have a quick response, but big enough to eliminate the ripple on the signal. And the full bridge rectifier can be replaced by a half bridge, since we are not consuming that much power, effectively reducing complexity and board space. Now each time we have 120 volts AC on our coil, the TPSU will quickly output a DC voltage. To isolate the mains from the rest of the circuit, we add an optocoupler and a resistor to the output of the TPSU. Optocouplers like the Pt.1 is just an LED and a phototransistor in a chip. When the LED shines, the phototransistor will get biased and current will start flowing from collector to emitter. With the appropriate circuit, you can sense the signal without the need to be galvanically connected to the mains. To finalize the high voltage part of our circuit, the anode of the LED is connected in series via a current limiting resistor to the output of the TPSU, and the cathode is connected to the negative pole of the filtering capacitor. This is the schematic of the circuit we've been building so far. The values were tuned to 120 volts AC levels. You may need to change some values if your mains levels are different. Reading the signal is another story. So far, we've only biased the transistor on our optocoupler. In order for a microcontroller to read this signal, we need to add a resistor at the emitter. That way, the emitter current creates a voltage drop on the resistor, registering a logic level high. Optocouplers are current-controlled devices. That means that the current at the output is dependent of the current at the input. With the circuit we assemble, the forward voltage is about 1.2 volts. According to the datasheet, this corresponds to a forward current of about 5 mA. The CTR, or current transfer ratio, at the input current is about 400%. That means that the output current in the phototransistor should be 20 mA. If our logic side is fed with a 3.3 volt supply rail, then the resistor at the emitter should be around 100 ohms. This produces an input voltage of about 2 volts, enough to be read as a logic high. After writing, I'm uploading this quick sketch to the microcontroller that will print out on the serial monitor the detection of AC voltage, we see that nothing gets printed when we press the button. The microcontroller was unable to read the signal. I tried raising the emitter resistance in hope of raising the signal level, but I chose to change it from 100 ohm to 200 ohm to no avail. So, confused, I removed the resistor and added a 3904 transistor in a Darlington configuration to increase the current, and by increasing the current, increasing the voltage at the emitter. The emitter of the 3904 was connected to a digital pin in the microcontroller and tied to ground via a 1K resistor. This is only a workaround for now. I intend to eliminate this transistor in the future. Testing this circuit with the same code, we get a quick and stable AC signal detection, without any bouncing. This solves the detection problem. Now onto the next one, processing and publishing. But before that, we should test the circuit on an actual doorbell. In my case, the doorbell was in an awkward position to reach in with a laptop, so I had to program in a sketch that would publish the number of times the microcontroller detected the signal via MQTT to my phone. This is the sketch I used. It's a slightly modified example sketch of the popular Arduino pop-sub library. For reference, the sketch is in the project page, link in the description. To test this, I've set up a Mosquito MQTT broker on a computer on my network. MQTT is a subject that warrants its own video. A few of my favorites will be listed in the description box. To keep it short and simple, MQTT is a way in which devices broadcast messages on specific topics to anybody listening that specific topic, also known as publishing and subscribing. MQTT requires a server or broker like Mosquito to keep everything in order, so we need to install it on a computer. After following the installation procedure of Mosquito, we're ready to publish messages. Testing the code on the same setup as before gave us positive results. The app I use on my tablet to read MQTT messages is called MQTT Dash, available for Android. I proceeded to install the circuit on my doorbell. First, I pulled the wires that were connected to the solenoid and attached some leads with some electrical tape. This feed directly to the main side of my board. The MCU was powered with a phone charger because we haven't defined how we're powering the board yet. As you can see, the board manages to send MQTT messages just fine. This leaves us with one last problem, low power design. This is probably the hardest part of the project and the last piece of the puzzle because we need to consider everything. Before we choose the battery, we need to define power consumption and life. And power consumption is defined after we define the operating principle of the sensor. What is the operating principle? Consider this. To maximize life, we need to force the sensor to sleep until there is a ringing event, where it wakes up and publishes a message to the broker. Ringing events are counted if there is a big enough gap of time between button presses. So if a visitor walks to the door and presses the button multiple times, pause for some time and press the button again, it should be recorded as 2 ringing events, even if the visitor presses the button more than 2 times. Why is this important? It will completely define the battery life. Because if the sensor were to wake up, publish the message and enter sleep mode, then it will miss the presses when cycling on and off. And if the sensor never sleeps, then the battery life will be abysmal. Let's define the vent time to be 10 seconds. When the bell rings, the device will wake up and publish a message and stay on for 10 seconds. If there are more buttons present within that 10 seconds, the timer will restart. If the timer reaches the 10-second mark after the last button press, it will enter sleep mode. If we assume 10 rigging events a day with a 10-second timer, then we get 100 seconds of operating time a day. Our microcontroller is the ESP8266. According to Expressive, the manufacturer of the microcontroller, the average power consumption is about 80 mAh, which will equal to the current consumption of 2.2 mAh at 3.3 volts a day and an energy consumption of 7.3 mWh a day. Per year is about 803 mAh and 2650 mWh. To supply power to these devices, we must choose a voltage regulator. Typically, you always choose between a linear power supply, where the battery can be estimated with a milliamp hour rating, or switching power supply, where battery life is dependent on the watt-hour rating. As you may have noticed, we can even compare them without choosing the appropriate battery. The best candidates so far are alkaline cells like AA batteries or lithium cells. Linear regulator can only lower the voltage. That means that they will work up until the battery voltage is close to the operating voltage. How close? Well, for the LDO variant, which stands for low dropout, it's pretty close. A single lithium cell will work just fine. The only problem is that a small part of the charge won't be used up, which is good for the health of the cell. How much energy we're leaving off? You can estimate it by looking at the discharge graph that plots the voltage of the cell over time at a fixed discharge current. Since the current is fixed, then the variation in voltage is analogous to the variation in power. And since it's plotted against the time, then the area under the curve is analogous to the energy in the cell. Intersecting the lowest current curve with 3.3 volts, we can look at a representation of the state of charge of the cell. The area to the left indicates the energy used up once it reaches the voltage, and the area to the right indicates the energy remaining in the cell. For AA alkaline batteries, it's a similar story, but because they are cheaper and quote-unquote disposable, using 4 cells will guarantee that they use up all the charge in the cell, since they are considered dead at 1 volt per cell. The dead voltage of the pack will be 4 volts, and thus above the regulated voltage. Now let's talk about the sleep current. According to Expressive, deep sleep current can get as low as 20 microamps. However, that's only the microcontroller. We still need to consider the current draw of all other components in our circuit. The popular AMS1117 linear regulator have a quiescent current of 5 milliamps, which is unacceptable. Better linear regulators will draw around 1 microamp, which is negligible. For switching power supplies, the story is different. Good ones have 15 microampere quiescent current, which will almost double the current draw when sleeping, which will now be 35 microampere. Not to mention that their efficiency is bad at those current draws. This is a win for the linear regulator, but I have an even better solution. Both linear and switching power supply have a built-in enable pin that will power on and off the regulator when toggled. The current draw of the regulator is still present, but on the tens of nanoampere range, which we will grossly round up to be 1 microampere, just to be extra safe. Let's call this mode hibernation mode. Since the power supply is off, the current draw from the microcontroller is 0. The only current draw comes from the regulator and the accessory circuitry. To be safe, let's assume a safe 5 microampere for both regulators. Now, how do we enter hibernation mode? Here's how. When the optocoupler gets a signal, T1 gets biased and C1 gets charged via T1 and R1. When the optocoupler is off, the charge is held and the voltage at T1's emitter should be close to VBAT. The enable pin is connected to this node, which turns on the regulator and the microcontroller and stays turned on for 10 seconds, processing any signal from the optocoupler. When the microcontroller is done, it activates T2 and will discharge the capacitor via R2. Once the voltage drops below logic level high, the microcontroller turns off and T2 deactivates. Now we are ready to decide and design our power supply. So far, we have to make 3 decisions: lithium versus alkaline, linear versus switching, or deep sleep versus hibernation. That's 8 scenarios. We could be more meticulous, but that's enough for now. The actual daily consumption is 100 seconds of 80 milliamps at 3.3 volts, and 86,300 seconds of deep sleep/hibernation. Running the number for each scenario yielded the following results, which were not that surprising. The top 3 combinations were lithium battery, linear regulator, and hibernation mode with 1,671 days, or 4.58 years. The second, lithium battery with switching power supply and hibernation mode with 1,593 days, or 4.36 years. And lastly, alkaline with a switching regulator and hibernation mode with 1563 days or 4.28 years. Although it may seem counterintuitive to see linear regulators perform better than their switching counterparts, it makes sense. The efficiency of a linear regulator is mostly determined by the voltage difference between input and output. It can be calculated by dividing the voltage output by the voltage input and multiply it by 100%. For lithium, the efficiency was about 89%, which was higher than the switching power supply efficiency at about 85%. For alkaline batteries, the efficiency of linear regulators was about 55%, which is horrendous, and way lower than the switching efficiency. It would seem like a no-brainer to go with the clear winner of this competition. However, the smarter pick will be the third place, and there are many reasons why. First, price. A 4000 mAh lithium cell from a reliable source will run about $10 to $15, compared to a common 4AA battery pack that would cost about $1 to $2, or even less. Sure, you can recharge lithium batteries every time they are discharged, and at that rate, your grandkids will have grandkids by the time you need to replace a cell. But think about it for a second. To justify a lithium cell at that price, you need to burn through 28 alkaline batteries, which will equal to 35 years. If you still think it's worth it, let me go through my other reasons. Second, self-discharge. According to Battery University, lithium batteries, a lithium ion and lithium polymer, loses about 5% of their charge within the first 24 hours without doing anything. After that, they lose another 4 to 5% each month. You won't even make it to the 2-year mark before needing to recharge. Alkaline, on the other hand, loses about 2 to 3% each year. And lastly, my third point, recharging. Even if we ignore the self-discharge problem we just brought up, when the lithium cell discharges, you still need to recharge it. This involves reaching the doorbell, removing the cover, unplugging the battery, setting it to charge, wait a couple of minutes or hours, reach the doorbell yet again, plug the battery in and close the cover. Maybe I made it sound more like a chore than it actually is, but compared to just swapping the alkaline batteries in a single go, it's clearly at a disadvantage. Also, how would you or anyone else like my parents charge the battery? You still need some sort of separate battery charger, since a bending one doesn't make sense, because charging the doorbell will imply a total disassembly of the circuit. Just ask yourself, are you building this for you or for someone else? To summarize our power design, the board will contain a switch mode step-down or buck power supply, and it will be powered by 4 AA batteries. When inactive, it will enter hibernation mode, and we are expecting a battery life of just above 4 years. The proper way to test this is using the actual chip we intend to use in our final version, but placing order takes a while, and without properly testing the hibernation circuitry, we shouldn't assume it's going to work. On my parts bin, I found a step-down switching power supply, based on the Texas Instrument LM2596. The model didn't break out the enable pin, so I had to solder a jumper to it. Upon reading the datasheet, this power supply is way out of spec. The standby current is about 80 microampere. Operating coordinating current is 5 mA, and efficiency is about 70%. This will yield a reduced battery life overall, but since it's a prototype, it wouldn't matter anyway. The biggest difference, and by far the worst offender, is that the enable pin in the power supply is an active low. That means that in order to enter hibernation mode, the pin must be held high. The hibernation circuitry we tested earlier was designed to operate with an active high, but that's okay, because swapping the triggering pin with the shutdown pin should work. Except it doesn't. Not only is the enable pin working backwards, it sinks way too much current that our buffer capacitor gets discharged in less than a minute, dropping the enable pin to low, which turns on the regulator. If this enable pin was active high, this bug wouldn't work as a feature, since it will automatically turn off the regulator after some time if the ESP froze and it doesn't turn itself off. To fix this, I added a MOSFET configured as an inverting buffer. The capacitor gets connected to the gate of the MOSFET, which ideally doesn't draw current. When the capacitor is discharged, the current at the drain is 0 and the voltage at the drain is high. When the capacitor gets charged, the gate to drain voltage is low, then the voltage at the drain is also low. After testing this, the capacitor can hold this charge for way longer, and if it discharges, it's a fail-safe instead of a fail-deadly. One thing to note is that our hibernation current is about 45 microampere. This is lower than the 80 microampere the datasheet states. We're not complaining though. At last, we solved our final design problem. We can jump right into prototyping. Testing was extensive. Many parts didn't work as planned, so I had to tweak, test, and retest many aspects of the design. But after many trials and tribulations, the circuit worked as intended. The system woke from hibernation when the button was pressed, registered every press without repeating, and entered hibernation mode after 10 seconds of the last press. At this stage, we can add and test many hardware features to augment the functionality of this project. The ones I'm planning to add are battery level sensor, wake up and shutdown buttons, and a programming switch. The battery level sensor will measure the voltage level of the battery using the analog pin on the microcontroller. For the ESP8266, we need to add a few components to make this possible, because it can only read from 0 to 1 volt, and the battery pack will have a maximum voltage of 6.5 volts, probably even higher. The easiest way to achieve this is by implementing a voltage divider that will scale the voltage to a readable level. To get a division by 6.6 with common values, we can use 5.6K and 1K ohm resistor. This introduces a problem. Voltage dividers constantly draws current. Increasing the values might sound like a reasonable fix for this, however high resistor values are susceptible to noise. Adding a few MOSFET to connect and disconnect the voltage divider solves the issue. This is the exact diagram Kevin Dara, electronics engineer and YouTuber, used in a similar project. Side note, this project was hugely influenced by him. You should check out his channel, link in the description. The other additions were pretty trivial. Use a few buttons that simulates the button press and shutdown signal. The programming switch is just a simple dip switch that the microcontroller will read as soon as it boots up to enter programming mode, disabling the shutdown signal. This enabled us to program the microcontroller without the need to disconnect it from the circuit. Testing these features went well. The voltage of the batteries was reported to an MQTT topic and monitored on my phone. The button did exactly what they were meant to do, and the switch was easily read by the microcontroller. The breadboard prototype looked like this. Not exactly the nicest thing to look at. The schematic of the prototype is the following. You can find it in the description for future reference. This is a sketch I wrote for this test. It is rushed and nowhere near finished. It will get a huge overhaul soon. Time for another test, this time the real test. We prop up the circuit next to the doorbell, attach the leaf we left connected from the previous test to the terminal blocks of the circuit, and power it up. As expected, everything worked perfectly. But that's only testing short term. We need to test long term functionality. It's very tempting to just leave the breadboard hanging from its wire or actually anchored to the doorbell and start designing the PCB. But the idea of leaving this somewhat heavy piece of metal hanging upside down, held only by focus, commitment, and sheer will make me feel very stressed. The obvious way to go around it is with barrel board and soldering. Lots of soldering. Not much to add here. The large number of parts speak for themselves. This will take some time, and that heavily depends on your soldering skill. Here are a few recommendations for beginners. Use flux core solder. Don't try to make it small. Plan ahead. Don't be afraid to use jumper wires, and always solder with your favorite music. After the breadboard prototype is finished, the project is ready for the big test, so I added some heavy-duty double-sided tape to the board and battery. Climb my ladder, stick it to the doorbell enclosure, and finish installing it the same way we did with the breadboard prototype. A quick test with the buttons, and the microcontroller wakes up and sleeps. Ringing the doorbell wakes the board up and publishes the message and goes to sleep shortly after. Let's call it a success and the end of part 1. In the following episodes, we will design and build the signed prototype, finalize the programming, revise the schematic, order and assemble some PCBs, and make some enclosures. Thanks for watching. If you enjoyed this video and find it useful, please consider liking and subscribing. Please feel free to point out any error and suggestion in the comment section, and I will address them in the next part. See you soon.